All right, so this time we're diving into Linux device drivers. It seems like someone wants to bend hardware to their will with Linux. And with what we're about to uncover, um, let's just say you'll be speaking fluent kernel very soon.
Yes, your excerpts from Linux device drivers are really a great place to start. It's not just a technical manual, but a look into the philosophies that shaped the Linux kernel.
Yeah, it's like seeing behind the curtain of Linux history. We're talking about Alessandro Rubini. He's the author of our source material. Not just an electronic engineer, but someone who really helped connect custom circuitry with, computers.
You can really see his influence right away.
Yeah.
Rubini doesn't just tell you how to write drivers. He explains the why, the principles that help you create elegant solutions. It's like that Unix philosophy really coming through.
You mentioned the Unix philosophy. Our source talks about this mechanism versus policy idea. It seems like a big concept. What does that mean in practice for, a driver developer?
It's about having different parts, creating a system that's both powerful and flexible. Imagine it this way. The driver provides the how, the mechanisms for your hardware to talk to the system, like a set of tools, the what, the policy, what you want to do with your hardware, that's all up to you, the programmer.
So the driver doesn't tell you what you can do, but instead gives you the tools to create your own solutions.
Exactly. That's what makes device drivers so versatile. Think about a custom graphics card. The driver provides the ways to draw pixels, handle video memory, and communicate. But it's your program that decides what's actually drawn, how to use the memory, so it creates the visual experience.
I see. That's a great example. Our source mentions loadable kernel modules. Sounds very modular. Can you explain why this approach is so important, especially for someone just starting with their own hardware?
Sure. Imagine you have this new sensor you're playing around with and keep changing the driver code. With these loadable modules, you can add or remove your driver while Linux is still running. No need to restart and recompile the whole kernel every time.
Wow, that's efficient. That would be a lifesaver for prototyping and experimenting. But before experimenting, we need to get our driver ready for the kernel, right? What about the compilation process? What are the essentials there?
Right, you have to teach it to speak fluent kernel. This means using specific compiler flags instructions for the compiler and kernel headers, which are like dictionaries, making sure your driver and the kernel are on the same page.
So no communication problems.
Right. And a key thing here is the kernel symbol table. It's basically a master list of vocabulary for the kernel. When your driver is compiled, it checks against this table. That way there are no duplicates. This prevents overrides or conflicts.
That's good to know. We won't break the kernel with, a function name that's wrong.
Yeah, it's about making sure everything works well together and preventing system crashes.
Okay, so our driver is speaking the kernel's language. How does it actually talk to the hardware? Our source mentions I/O ports and I/O memory. Can you explain those a little bit?
Well, think of I/O ports like mailboxes. Each port has its own address. The driver can put specific instructions for the hardware in them. It's a very direct way to communicate, good for simple commands and quick updates.
So it's like sending a postcard. It's a short message to a specific place. What about I/O memory?
That's more like a shared whiteboard. The driver and the hardware can both read and write to certain places in the memory. This lets them exchange more complicated data and stay in sync.
I see. So depending on what needs to be done, the driver chooses the right communication method, postcard or whiteboard. What happens when the hardware has something important to tell the kernel?
Well, that's when interrupts come in. It's basically the hardware sending a signal flare to the kernel. This is really important for things that need to happen immediately. For example, let's say you have a network card driver. Every time a new packet comes in, the hardware raises an interrupt. This tells the driver to handle it right away.
So without interrupts, we'd have to wait for the driver to check for new data all the time. That would make for a slow network.
Exactly, like waiting for a letter in the mail when you need an answer right now.
Very slow and painful. But even with good communication and interrupts, we know that bugs are a part of software. What are some ways to debug that driver developers need to know?
Well, it's like detective work. And print statements are like our magnifying glass. We use them to put messages directly into the kernel log. That way we can see what our driver is doing, understand how it works, like asking it, what were you thinking when something goes wrong?
So we're leaving breadcrumbs for ourselves. What about the proc file system? The source mentions it. What's its role in debugging?
Think of proc_frms, like a window into the kernel. It shows you what's going on inside, including your device driver. It's not a normal file system, more like a live view of the kernel. You can access all sorts of information process stats, memory usage, even driver details, all through files and directories.
Like a live dashboard for the kernel.
Exactly. By looking at the files for your driver in proc, you can learn a lot about how it's behaving, what resources it's using, and any problems that might be coming up.
Interesting. Proc sounds like it deserves its own deep dive sometime. But for now, let's talk about a driver's ID, the major number. The source seems to think it's pretty important. Is this like a driver's social security number? Something that sets it apart?
More like a dedicated phone line, ensuring the kernel can always reach it. Each driver needs a unique number to prevent mix-ups. Older Linux kernels made you choose an unused number and register it manually. Modern kernels are much simpler.
So how do we get our driver its phone line in the modern world?
We use the registers_dev function. This lets you ask for a major number when the driver is loaded, and the kernel assigns it for you. No more manual allocation headaches.
That's a relief. What about device files in the dev directory? The files that act as gateways to our hardware. Are those created manually?
Back in the day, you'd have to create them yourself with commands like mado. It was a bit tedious. Thankfully, Linux introduced devs, the device file system. It automatically creates and manages these device files, like an automated construction crew.
That sounds much easier. One less thing to worry about. Let's talk about how our driver and the system interact. The source mentions file operations. What's exciting about a term like that?
Don't be fooled by the name. This is where the action is. File operations determine how your driver works with the system, outlining what it can do. Think of them as system calls or commands that your driver understands, opening and closing the device, reading data, writing data, everything.
So it's like the driver's instruction manual, all the actions it's programmed to do.
Right. These file operations are defined within a file operations structure. Think of it as a table of contents. It connects each system call to the correct function in your driver. When the kernel needs something done, it checks this table to find the right function.
An organized system. What about this file structure mentioned in the source? We have file operations. Do we need another file concept?
But the file structure is different. This one, called struct file, represents a connection to your device that's already open, like a communication channel between a user's program and your hardware. This structure stores important information about that connection, such as the file descriptor, the access mode, even a pointer back to the file operations structure.
So the driver keeps track of each active connection.
Exactly. Every time a program opens the device file, the kernel makes a file structure to keep tabs on that connection. You can even store device-specific info in it, customizing how it works for each user.
Like personalized settings for each user. Neat. What happens when they're done and want to disconnect? How does the driver close the connection?
That's the release function's job. It's part of our trusty file operations structure.
Right.
And gets called when the last instance of a file is closed. It's the driver's cue to clean up, let go of resources held by that connection, and basically say goodbye.
So it's the driver's way of saying thanks for stopping by and getting ready for the next connection. Now the source delves into data transfer with a curious example, the Skull driver. What's with the name?
Skull, short for Simple Character Utility for Loading Localities, might sound odd, but it's a classic tool for understanding character device drivers. It's a virtual device, a safe space for driver developers to practice data transfer without touching real hardware.
A driver boot camp.
Exactly. Skull lets us experiment with how data flows between user applications in user space and the kernel in kernel space.
User space and kernel space, two different worlds in Linux. Why is it important to differentiate them when talking about drivers?
Imagine this. User space is like a city, applications going about their business. The kernel is the city's infrastructure, power, water, traffic, keeping things running smoothly.
So user space is the hustle and bustle, and kernel space is the behind-the-scenes operation.
Yes. And just like you don't want anyone messing with the city's power grid, you need tight control over data moving between user and kernel space.
Safety first. But how do we manage this data exchange? The source mentions read and write functions. Sounds straightforward enough.
These functions are our customs officers. They carefully inspect and transfer data. Let's say a user wants to send data to the device. They use the write system call, which reaches your driver's write function. This function takes the data, packages it properly, and sends it off to the hardware.
A secure courier service, making sure data arrives safely and correctly.
That's it. And the read function works the opposite way, retrieving data from the hardware and sending it back to the user space.
This is really interesting. But even with secure couriers, we need a common language. What happens when user and kernel space have different ideas about memory addresses or data structures?
That's where things can get tricky. A valid address in user space could mean nothing in kernel space. That's why the kernel has special functions for this, usually in a header file called asmuaccess.
So they're like interpreters, making sure both sides understand each other.
Exactly. Functions like copyTozer and copy from user translate between the two, making sure the exchange is smooth and safe.
No communication breakdowns then. What about when we want to go beyond basic read and write, like sending commands or adjusting settings? Our source mentions ioctl. Is that the key?
You got it. ioctl is our secret handshake. It's a way to add more to what our driver can do beyond those basic operations. It lets user programs send special commands, basically giving our driver hardware communication more words to work with.
So we're adding new skills to our driver's toolkit, allowing for more control and customization.
That's the idea. You can configure settings, trigger actions, get detailed status, tons of possibilities, really. It all depends on your creativity and what the hardware can do.
That's amazing. Sounds like ioctl gives us a direct connection with the device, but with great power. No. How do we ensure only authorized users can use these advanced features? The source mentioned something called backward compatibility. Why is that important, especially with Linux always changing?
Backward compatibility is about keeping our driver friends with older kernel versions. Linux is always evolving, getting new features and upgrades, but we don't want our driver to suddenly stop working just because the kernel got a new look. Right.
That would be awful. It's like our driver suddenly forgetting how to speak the language. So how do we make sure our driver can keep up with future kernel versions?
It takes adaptable and forward-thinking code. One way is conditional compilation. We can check the kernel version during compilation and include or exclude specific code parts as needed. It's also crucial to really understand the kernel's API documentation. Knowing what might change or disappear in the future helps us write code that can handle it.
So our driver becomes multilingual, able to speak different versions of the kernel language.
Exactly. By keeping backward compatibility in mind, we can create robust drivers that can adapt to the constantly changing world of the Linux kernel.
That's good to know. It's like our driver has a crystal ball, able to see into the future of the kernel. But let's come back to the present and debugging. We've talked about print and proc, but our source also mentions strace. What does that bring to the table?
Think of strace as a surveillance system. It records every little thing our driver does at the system call level, what functions are called, what arguments are passed, what comes back, all logged in detail.
So if print is our driver's diary, strace is the hidden camera.
Precisely. Strace helps us spot weird behavior, find the source of errors, and get a much clearer picture of how our driver talks to the system.
This is getting really interesting. But sometimes things still go wrong. Maybe our driver panics, causing the system to crash with those cryptic oops messages. What can you tell us about those?
Oops messages are the kernel's way of saying, we have a problem. They pop up when the kernel finds a critical error, something like invalid memory access or forbidden operation. They might look like gibberish, but they contain valuable clues.
Like a kernel crash report, a digital autopsy.
That's a good way to put it. They tell us about the problematic instruction, the contents of processor registers, and the stack tracer trail leading back to where the issue began.
So how do we decode these messages and find the culprit? Do we need, like, a kernel whisperer?
Luckily, we have Claude, the kernel log daemon. It keeps an eye on the kernel log and tries to make sense of those oops messages. It translates them into something we can understand.
So Clogged is here to decipher the kernel's cries for help.
Exactly. It's really helpful for figuring out what went wrong in a kernel crash. But even Clogged needs some help sometimes. If we load our driver after Clogged has already started, it might not have all the info about our driver's code. Remember the kernel symbol table.
Right, those symbols are like name tags for our driver's functions and variables. Clog uses them to connect the dots. How do we make sure Clogged has the most up-to-date information?
We send Clogged a signal, like a quick heads-up, specifically the SysR1 signal. This tells Clogged to reload its symbol table, making sure it knows all about our driver.
Like saying, hey, new driver in town, update your records. The source also mentions GDB, the GNU debugger, another tool in our kernel debugging kit.
GDB is like a time machine for our driver code. We can pause execution, rewind, replay. It gives us amazing control when debugging.
So with GDB, we can step through our code line by line, see what's in memory, even change things as we go.
Exactly. And for kernel debugging, you can use GDB with something called a core file.
Core file. Is that a snapshot of the kernel's memory when it crashed?
Yes. It captures the state of the system at the exact moment of the crash. By loading this core file into GDB, we can travel back to the crime scene and analyze everything.
Wow, it's like CSI for our kernel. Using GDB with a core file sounds pretty advanced. Are there simpler kernel debuggers, especially for beginners?
Of course. Think of GDB as the high-tech lab and KDB, the integrated kernel debugger, as the trusty field kit. It's built right into the kernel and is accessible through a serial console. Much more straightforward to use.
No need to install anything extra. We can jump right in and debug.
That's the idea. With KDB, you can examine memory, peek at registers, even change data structures directly. Very powerful for understanding the kernel.
Convenient. But I imagine there are risks, especially with those direct modifications.
Absolutely. Caution is key. KDB is powerful, but one wrong move can mess up the kernel state and create even bigger headaches.
Right. Handle with care. The source also mentions a patch called IKD, the Integrated Kernel Debugger. Is this a competitor to KDB, or do they work together?
Think of IKD as a powerful upgrade for our debugging tools. It's an unofficial patch, mostly popular on x86 systems, that adds a bunch of advanced features.
So more options and features for our debugging toolkit.
Exactly. IKD offers breakpoints, pausing at specific lines, stack tracing, seeing the flow of function calls, and even a way to visualize the kernel's call graph, how functions connect.
A call graph sounds incredibly useful. Seeing how everything in the kernel relates to each other would be fascinating. But if IKD is unofficial, does that mean it's less reliable or supported?
It's something to keep in mind. IKD is powerful, but not officially supported by the kernel developers. That means it might not always work with the newest kernel versions and could have some quirks.
That makes sense. Experimental tools sometimes come with extra challenges. The source mentions user mode Linux, or UML. Is this a parallel universe where Linux runs inside itself?
You're on the right track. UML is like having a tiny Linux system within our main Linux system, a kernel in a bottle, if you will. It lets us run a whole Linux kernel as a user space process, a safe and isolated space for trying things out.
So it's like a virtual sandbox for kernel developers to test new things without affecting the main system.
Precisely. UML is great for testing kernel features, experimenting with different settings, even debugging drivers, all in a controlled way.
That sounds incredibly useful. No more worrying about crashing the whole system with a buggy driver. But there must be limitations. Can UML access real hardware?
That's the catch, at least for driver development. Currently, UML can't directly interact with the host system's hardware.
It's like having a fully equipped workshop but not being able to use the tools on actual projects.
Good analogy. UML is fantastic for testing our driver's logic and debugging it. But eventually, we have to try it on a real system to see how it behaves with physical hardware.
Simulations are helpful, but nothing beats the real thing. Still, UML sounds invaluable for catching those early bugs. Let's get back to driver interaction and IOCL, our secret menu for advanced communication. The source highlights using IOCL effectively. What are some key things to remember?
With IOCTL, organization is key. It uses command codes and numerical IDs for different operations. To keep things clear, we need a good system. The source recommends a 4-part structure, like a code for our driver's commands.
A 4-part code. Tell me more.
Imagine each part is like a piece of an address guiding our command. The first part is the magic number. It's unique to our driver, making sure we're talking to the right device.
So if our driver's magic number is, say, 777, all its IOCTL codes would start with that.
Right, like a driver's license plate identifying where it came from. Then there's the ordinal number. This tells us which specific command it is, like a serial number for each command.
So magic number 777, ordinal 1, is different from magic number 777, ordinal 2. Got it. What about the other 2 parts?
The third part acts like a traffic signal. It tells us if we're sending data to the driver, getting data back, or if it's a two-way exchange.
So specifying if our command is delivering, receiving, or having a conversation with the driver.
You got it. The last part is the size field. It's like choosing the right size box for a package. It tells us how much data is involved in the command.
We don't want our data spilling out because we use too small of a container. This structure for IOCTL codes makes sense. It's like a well-organized filing system for our driver, preventing mix-ups.
Exactly. And it's even more important when you think about security. We don't want just anyone changing our driver settings or getting to sensitive data, right?
Definitely not. Like having a bank vault, we need serious security. How do we control access to these IOCTL commands? Is it as simple as checking for root access?
While root access is powerful, relying only on that for IOCTL control isn't the best idea. It's like giving everyone the master key. Thankfully, Linux has capabilities.
Capabilities. Now that sounds interesting. So it's about having specific permissions for specific tasks.
Yes. Think of it like granting special abilities without giving full control. It allows for much finer control. We can give out only the necessary permissions for a specific job.
Much more secure that way. So how do these capabilities work with our ioctl commands? Do we check for certain capabilities before running certain commands?
Exactly. The kernel provides a function called capable. We use it to see if the process making the request has the necessary capability. For example, you might need a specific capability before changing important device settings.
Like a security checkpoint, making sure you have clearance before entering.
Exactly. This careful control over ioctl is crucial for keeping our driver and the whole system secure. Sometimes we need to restrict access to the whole device, not just certain commands. The source mentions something called controlling access by write. How does that work? Let's say you have a robotic arm controlled by your driver. Writing to its device file isn't about sending data, but about issuing commands: move here, grab this, release that. Controlling access by write lets us choose who can send these commands, basically who's in control.
It's like having a safety switch on the robotic arm.
Exactly. This is useful for devices where the interaction is more about control and less about data transfer in the traditional sense.
That makes sense. But as we talk about all this, it's clear that timing is crucial. How does our driver handle requests that might take a while, especially with hardware that doesn't always respond instantly? The source mentions blocking and non-blocking operations. Can you explain?
Imagine you're at a restaurant. In a blocking situation, you order your food and wait at the table until it arrives. Your world is on hold until your food is there.
Okay, so that's blocking, waiting patiently for the task to be done. What about non-blocking in this scenario?
Non-blocking is like placing a to-go order. You order, get a number, and go about your business. You can check back later or wait for them to tell you it's ready.
So placing a to-go order, you're not stuck waiting. You can do other things.
Exactly. With device drivers, choosing blocking or non-blocking depends on the device and what the application needs.
So a blocking operation is like sending a file to the printer and waiting for it to finish. Non-blocking is like sending the file and immediately moving on, maybe getting a notification when it's done.
You've got it. Knowing how to use both is key to creating drivers that are efficient and responsive.
This is really making sense now. But how does a process know when a non-blocking operation is finished? Does it have to keep checking back with the driver?
There's a better way wait queues. Remember those queues that allow processes to wait for specific events?
Right, like taking a number at the deli counter?
Exactly. With non-blocking operations, a process can add itself to a wait queue related to that operation. When the operation is done, the driver notifies the process that the results are ready.
Like the deli counter buzzing when your number is up. What about those times when our driver needs to wait for a specific event, like new data from a sensor? Our source mentions asynchronous notification, like setting an alarm for our driver.
You could say that. Instead of the driver always checking for new data, which can be inefficient, asynchronous notification is like saying, hey, let me know when something happens.
So it's like having a motion sensor instead of someone constantly staring out the window.
Precisely. It's a much smarter way to do things. A common method is using signals, which are like software interrupts sent to a process.
Like a text message to the driver, new data alert.
Exactly. The driver uses signals to tell a waiting process that something happened or new data is ready. This way, the process can rest until it's really needed, making everything more efficient.
That's much better than constantly checking for updates. But how does a process sign up for these notifications?
Usually through a special ioctl command, or by setting a flag in the file structure. The process basically says, hey, keep me updated if anything interesting happens.
Like subscribing to driver updates. Now, back to access control. The source goes deeper into this, talking about control on a device file. How is that different from capabilities?
Think of it this way. Capabilities are like system-wide control. Access control on a device file is like having a guard at the entrance of a specific building. It's an extra layer of security just for our driver and its hardware.
Building a fence around our driver's territory, only letting authorized guests in.
Right. And we're not limited to just user IDs or group memberships. We could grant access based on things like a specific hardware key or a valid software license.
A flexible security system. So how do we set up this special access control? Do we add checks within our driver's functions, like verifying a license key?
Exactly. We can put these checks inside functions like open, read, or write. Before doing anything, the driver checks if the caller has the right permissions. If not, access denied.
It's like having a bouncer at a club checking IDs.
You got it. This allows for a much more adaptable and customized security system. Now let's talk data flow. Drivers often handle a lot of data, especially with high-speed devices. Our source talks about input and output buffers. Why are these so important? Are they like preventing data traffic jams?
Yeah, like those buffers are there to keep everything moving smoothly.
Right, they make sure data flows nicely between the driver, the hardware, and the applications.
So they smooth out any bumps and keep things consistent.
That's a good way to put it. Imagine you have a fast network card getting lots of data packets. Without an input buffer, they might come in faster than the driver can handle them, and then you'd have dropped packets and data loss.
So the input buffer is like a waiting area, making sure no packets get left behind.
Right. And then you have output buffers doing the same thing, but in the other direction, from the driver to the hardware. If the driver's sending data faster than the hardware can keep up, the output buffer acts as a temporary storage space. This prevents data loss and keeps the transfer smooth.
Like a departure lounge at the airport, making sure everything is ready to go.
Exactly. And these buffers aren't just about storage space. They're also really important for synchronization, making sure data is accessed and changed in the right way.
Synchronization. It's like we're choreographing a dance between the driver, the hardware, and the applications. Everything has to be in sync.
That's a great way to think about it. Synchronization is all about making sure that everyone's on the same page when it comes to these shared resources, like our data buffers. It prevents conflicts and makes sure the data stays accurate.
How do we avoid those data collisions and keep everyone in line? The source mentions something called a semaphore.
Think of semaphores like traffic signals. They control access to shared resources, like those buffers we were talking about. They act like locks, ensuring only one process can access the data at any given time.
So if one part of the system is using the data, the semaphore is like a red light telling others to wait.
Exactly. And when it's free, the semaphore turns green and the next process can go. It's a simple system, but it really helps prevent data from getting corrupted. We want to avoid those race conditions.
Race conditions, those don't sound good. What are they?
Imagine two chefs trying to make the same dish at the same time, but they don't know what the other one's doing. Chaos.
Yeah, that wouldn't end well. So race conditions happen when different parts of the system try to access and change shared data at the same time, potentially messing things up.
Exactly. And semaphores help us prevent that by carefully controlling how and when shared resources are accessed.
That's good to know. We've already talked about asynchronous notifications, but the source also mentions wait queues. Are they related to this?
You could say that. With asynchronous notifications, we're sending a message when something happens. Wait queues are more about waiting patiently for your turn.
Like taking a number and waiting at the DMV.
Exactly. If a process needs to wait for something to happen, like new data showing up in a buffer, it can add itself to the right wait queue. It's a lot more efficient than constantly checking if the condition is met, which can waste time and resources.
So it's about saving energy and only taking action at the right time.
Exactly. And the kernel has a very good system for managing all of these wait queues, ensuring that processes are notified as soon as the thing they are waiting for happens.
So it's like our driver saying, okay, I'll take a nap. Wake me up when something interesting happens.
You got it. The source also mentions blocking right. Any idea why this specific type of blocking is important?
Is it about making sure that what's written actually gets written? Like making sure the data is saved on the device before moving on?
You nailed it. With blocking right, the process waits patiently until all the data has been fully transferred to the device, like handing someone a package and watching them lock it away safely.
That makes sense, especially for important data that needs to be written correctly. What if the device is slow or there's a problem with the connection? Do we just wait forever?
That's where timeouts come in. We can tell it how long to wait for the operation to finish. If it takes too long, the driver gives up and returns an error code, letting us know something's wrong.
Like setting a timer. And if the package isn't picked up by then, we know something's off. Now, the source mentions something called Jiffies. Sounds like something out of a children's book.
You're right, it's not about magical creatures or anything. Jiffies is how the kernel keeps track of time. It's a counter that's always ticking, measuring how time passes from the kernel's point of view.
So it's the kernel's own internal clock. But how does that relate to real-world time?
The speed at which Jiffies increases, something called the HD's value, can be changed. It's usually set to 100 or 250 ticks per second. It's like choosing how precise you want your stopwatch to be. A higher EZ means more accurate time measurements, which can be really important for certain operations.
So Jiffy's is our super accurate kernel clock. But what if our driver needs to take a break, to wait for something to finish? The source mentions ways to add delays. What are some common methods?
Well, one way, although not the most graceful, is the busy loop. Imagine watching a pot, waiting for the water to boil.
So the driver just sits there, checking over and over if the thing it's waiting for has happened.
That's it. It's not really efficient because it's using resources without doing any real work. But for very short delays, it can be okay.
Right, so what about longer delays where we need a better approach? The source mentions task queues. What are those?
Think of task queues as a to-do list. We can schedule tasks to be done later, which frees up the driver to do other things.
So it's like delegating tasks to be done later so the driver doesn't get bogged down?
You got it. We make a task queue, add our tasks to it, and the kernel takes care of them when it has some free time.
Much better than waiting for each task to finish one by one. The source also mentions something called the immediate queue. Is that a special kind of to-do list?
Think of it as the express lane for tasks. Anything put in this queue is treated as high priority and done as soon as possible, usually at the next timer tick.
So if our regular task queue is the regular line at the post office, the immediate queue is like sending something express mail.
You got it. It guarantees those time-sensitive tasks are handled quickly. Sometimes, though, we need even more control over timing, like if we want to schedule things for specific times. That's what kernel timers are for.
Kernel timers, like setting an alarm for our driver.
Exactly. We create a timer, set it for a specific time, and tell it what function to run when that time comes. It's like an alarm clock for our driver, reminding it to do something.
Very handy. Speaking of staying on schedule, we need to ensure our driver has the resources it needs, especially memory. We've discussed Comalec and vmalec, but our source talks about some more specialized ways to get memory. One is get zeroed page. Why is it useful to have a page that's all zeros?
Imagine you're starting a new painting, but the canvas still has traces of the last painting on it. Those leftover marks might mess up your new artwork. Get zero page is like getting a brand new canvas. It allocates a page of memory and wipes it completely clean, setting everything to zero.
So it's about making sure our driver's memory is completely fresh with no leftover data.
Exactly. This is really important because that memory might have been used by other parts of the system, and we don't want our driver getting confused by any old information.
Cleanliness is key. But what if one page of memory isn't enough? We've got get free pages, right?
Right. If Get Zeroed Page is like getting a single hotel room, Get Free Pages is like booking a whole suite. It lets us allocate several pages of memory next to each other, which we might need for things like storing large amounts of data.
So get free pages is there when our driver needs some extra space to stretch out. Now, what about when our driver has to work with hardware that uses DMA? Does memory allocation come into play there too?
It definitely does. With DMA, the physical location of our memory really matters. The DMA controller needs to be able to find and access that memory easily.
It's like making sure your address is within the delivery zone.
Exactly. The kernel has functions like plulock coherent that not only give us the memory, but also make sure it's in a place the DMA controller can work with.
Wouldn't want those DMA deliveries getting lost. Now, our source mentions a function called IRMAP. What's that all about?
Think of IRMAP as a translator between the physical world of memory and the virtual world that the software uses. It lets us create a virtual address that points to a real physical location in memory. This is really useful when working with memory-mapped hardware.
Memory-mapped hardware? That sounds interesting. What's that?
Lots of devices, especially ones that need to communicate really fast, have their settings and controls mapped directly into the system's memory. ERMAP helps us access those physical memory locations, but instead of using physical addresses, which can change, we get to use a stable virtual address.
So it's like having a permanent forwarding address so our driver can always find the device, even if it moves around in memory.
Exactly. And that brings us to consistent memory. Any thoughts on what that might be?
I'm thinking it might be about making sure everyone has the most up-to-date information.
That's a great way to put it. Consistent memory is all about making sure that when something changes in memory, everyone sees that change immediately. That includes the DMA controller.
So it's like a shared document where everyone sees the latest version in real time.
Exactly. It's really important for DMA because we want to make sure the data being transferred is accurate and up to date.
No outdated DMA surprises. And when we're finished with the DMA operation and don't need that consistent memory anymore, We use DMA-free coherent to release it.
Precisely. We always want to clean up after ourselves and give those resources back to the system. Which brings us to bus mastering. Have you heard of this technique?
It sounds like we're giving our device the keys to the kingdom.
In a way, you are. Imagine a highway. Most devices are like cars, following the rules of the road. The CPU controls the flow of traffic. But with bus mastering, we're giving certain devices the power to direct traffic themselves, which can make things much more efficient.
So it's like letting the device with the most important cargo choose the fastest route.
Exactly. It's about giving some devices, like fast network cards or hard drives, the ability to manage their own data transfers. That way, the CPU doesn't have to micromanage every single detail, and it can focus on other tasks.
That makes sense. But it sounds like it could lead to accidents if we aren't careful.
You're right. Not all devices can handle that much responsibility. Bus mastering is usually reserved for devices that are designed to manage bus access and ensure data integrity.
It's like only giving experienced drivers a commercial driver's license. Now, what about scatter-gather DMA? That sounds interesting.
Imagine a delivery service that needs to drop off packages at multiple locations. It wouldn't be efficient to go back and forth to the depot every time, right? It's much faster to plan a route that hits all the stops in one go.
That's efficient routing. So scatter-gather DMA is like optimizing data deliveries, transferring data to or from different memory locations all at once.
Exactly. It's super useful when working with data that's spread out across different memory addresses, like large files or network packets.
So the DMA controller becomes a master planner, optimizing those data routes. But keeping track of all those different memory locations sounds complicated. How does the driver handle that?
That's where the scatter-gather list comes in. It's basically a map for the DMA controller. It tells it exactly where to pick up and drop off data, listing all the memory addresses and the sides of each data chunk.
It's like a detailed itinerary, ensuring all those data packages reach the correct destinations.
You got it. This scatter-gather list is how we tell the DMA controller exactly what to do, and it handles all those data movements efficiently.
This has been a fascinating look into the world of DMA. But all of this makes me think about hardware compatibility. Our source emphasizes that things like DMA and bus mastering can be very different depending on the hardware. How do we make sure our driver can work with lots of different hardware?
That's where abstraction layers come in.
Abstraction layers. It sounds like we're building a protective bubble around our driver.
That's a good way to think about it. Abstraction layers simplify things by providing a standard interface for common hardware tasks. That way, our driver doesn't have to be an expert on every single piece of hardware it encounters.
So it's like having a universal translator for hardware.
Exactly. The Linux kernel has different abstraction layers for various types of devices like PCI, USB, and network devices. This makes it much easier to write drivers that work with lots of different hardware.
That's a huge help. We don't want to have to write a new driver for every device on the market. Speaking of devices, the source mentions something called platform devices. What are those?
Think of platform devices as the miscellaneous category of the hardware world. They are the unique snowflakes that don't neatly fit into those standard categories like PCI or USB. Maybe they're integrated directly onto the motherboard, or they're just unusual in some way.
So platform devices are the rebels of the hardware world doing their own thing.
That's a fun way to think about it. And Linux has a platform device framework to help us manage these unique devices.
It's like the kernel has a special section in its rulebook for those who like to break the mold. Now, sometimes our driver needs a little help from its friends, right? They might need to access a file, get more memory, or even send a message across the network. Our source talks about kernel services. Is this like our driver calling for backup?
Exactly. Kernel services are like a team of specialists ready to help our driver whenever it needs something.
So it's like having access to a whole bunch of experts, each with their own set of skills, ready to lend a hand.
Precisely. There are services for everything. Managing memory, using the file system, networking, even keeping track of time.
Our driver has a whole team of assistants, but how does it ask for help?
The kernel has a set of functions that our driver can call. Each function is like a request for a specific service.
So it's like filling out a form, I need assistance with, and then the kernel takes care of it.
Exactly. The kernel is really good at handling these requests and making sure our driver gets what it needs. One specific service mentioned in the source is module loading. What's that all about?
It sounds intriguing.
Imagine this. Our driver needs to talk to a brand new, super fast wireless card. But the code to handle this particular card isn't part of the core kernel. What do we do?
Sounds like we need to call in a specialist.
Exactly. That's what module loading lets us do. We could load extra code modules into the kernel while it's running, giving it new abilities on the fly.
So our driver can assemble a whole team of experts, each one ready to handle a different task or device.
You got it. And these extra code modules are only loaded when they're needed, which saves resources.
That's awesome. So how does our driver request these specialized modules?
There's a function called request module. Our driver tells the kernel the name of the module it wants, and the kernel does the rest.
It's like putting up a job ad. Driver seeks module fluent in wireless communication protocols. Must have experience with the latest hardware.
I love that analogy. The kernel is like the ultimate headhunter, always able to find the right module for the job.
This has been an amazing journey, but as we've seen, the world of drivers is constantly changing. New things are added, old things become obsolete. Our driver needs to keep up.
You're absolutely right. The Linux kernel is always evolving. And as driver developers, we need to keep learning and adapting. We need to keep an eye on kernel updates, new features, and potential compatibility issues. The kernel developers do a great job of making sure things work with older versions, but we still need to test our drivers carefully and be ready to make changes.
So it's not just about writing the code, it's about staying curious and adaptable in a constantly changing world.
Exactly. The world of Linux device drivers is full of challenges and opportunities. If you stay curious and are willing to learn, you can create drivers that work seamlessly with today's technology and are ready for the future.
That's inspiring. As we wrap up our deep dive into the world of Linux device drivers, what's the one thing you'd like our listeners to take away from all of this?
Remember, you have the power to shape the digital world. Don't be afraid to explore, experiment, and try new things. The Linux kernel gives you everything you need to make your hardware ideas a reality.
That's a fantastic message. And remember, every expert driver developer started as a beginner, figuring things out one line of code at a time. So grab your keyboards, dust off those circuit boards, and let the driver development begin. Thanks for joining us. Until next time.